Hello, students, and welcome to our very last major academic unit on spectroscopy. I hope you enjoy this unit. It's actually one of my favorites. We're going to do some interesting stuff. There's going to be some puzzles and some things for you to work on. I do need you to know that this is some challenging stuff, and you will need to spend some time and effort and energy on this unit and try to keep up because there's some interesting stuff here that you probably haven't seen before. We're taking a break from reactions. This is stuff that's sort of new, but you will need to apply some energy and effort for this. So do the best you can, and we're going to jump in. One of the things that I love about spectroscopy is that it's actually everywhere. And we don't always call it spectroscopy, but this technology is in use pretty much anywhere you go. So, for example, if you've ever had any sort of medical scans, if you've had an X-ray, if you've had an MRI or a CT scan or a PET scan or any of those sorts of medical imaging, that's basically a form of spectroscopy. You see it in everyday life. Passing by, you might not know what this gentleman is doing. He's not mowing the grass, but this is a ground penetrating radar. So this is a way to use imaging, spectroscopy, a form of spectroscopy, to figure out what's going on underground, to find pipes and utility lines. Over here on the left, if you've ever flown in a plane, the lovely TSA agents might have asked to swab your hand or swab the inside of your backpack. What they're doing is spectroscopy. They're using a mass spec or an ion scanner here to look for particular residues of chemical compounds. So that's an example of spectroscopy in action. If you have one of these key fobs that unlocks your car automatically or allows your car to drive without inserting a physical key, that's not exactly spectroscopy, but it's definitely a related technology. And finally, down here in the bottom right, this is an image of the Earth and looking at different temperatures. And so you can use any of the sort of ways that we image or look at the Earth in terms of looking at carbon dioxide in the atmosphere or water vapor in the atmosphere, looking at temperatures, looking at weather patterns. Those are also a form of spectroscopy. Basically, anytime someone is doing a scan or some sort of imaging, if you watch science fiction at all or read science fiction and they talk about scanning something where the sensors are on maximum, what are they scanning? They're scanning the electromagnetic spectrum typically. So these are sort of science fiction applications of spectroscopy. So even though a lot of the spectroscopy that we're going to be doing is going to look a little bit more like this in the upper left, there will be examples and different applications of spectroscopy everywhere you go, and only more so, just increasing in the future. Let's spend a few minutes talking a little bit about what spectroscopy really is. The word spectroscopy, of course, comes from two word parts: scopy, meaning viewing or observing, and spectro, in this case referring to the electromagnetic spectrum. So basically all the different forms of light. In a basic spectroscopy experiment, you have some sample that you're trying to look at. That in this case is just a beaker. So you put your sample in here. You have some sort of light source that may or may not be a physical flashlight with light in the visible range. Sometimes it is visible light. Sometimes it's ultraviolet or infrared or microwaves or radio waves. So there's lots of different types of light sources. And then on the other side, there's some sort of detector. And that detector might be a literal physical eyeball, or sometimes it's an electronic eye, some sort of imaging sensors or photomultiplier tube or something that will detect the light that is inbound. Spectroscopy is basically at its heart about observing the interactions between light and matter. And those interactions can be different depending on what type of light we use. If we use light in the ultraviolet and visible range, you're talking about basically causing the electrons to become excited, to jump from their ground state up to some higher excited state. If you use radio waves, you can induce what is called nuclear spin excitation. Basically, the nucleus of many atoms can act like a little magnet. It has a particular spin, And if you blast it with radio waves, you can change that spin, cause the spins to flip around. If you shine infrared light on many atoms, you will cause the bonds to bend and stretch. Sometimes this heats them up. Sometimes there's an associated transfer of thermal energy in that way. In all forms of spectroscopy, if you compare the light emitted from the source and you compare that to the light that's being received by the detector, you can figure out how that light is being changed as it interacts with the atoms and molecules in the sample. And that's useful. It can sometimes tell you what is the identity of those molecules in the sample. Let's say you thought you made some, 3-bromopentane, but you're not sure. You can use spectroscopy to figure that out. It's also sometimes useful to actually figure out some information about the behavior of the molecules and see what it is that they're actually doing in that sample. Oh, there's my kids. And it looks like my son has a question. He says, wait, how can light interact with matter? Remember, these things are different, right? When we're talking about light, we're not just talking about Roy G. Biv. We're talking about everything in the electromagnetic spectrum. But this light is not the same thing as matter, right? For matter, we're talking about atoms and molecules, protons, neutrons, and electrons. Light, we're talking about an oscillating electromagnetic wave. But these things can actually interact with each other in a number of different ways. And of course, his big sister, Piper, she's kind of a know-it-all. It's a little bit complicated, but there's lots of different ways that light and matter can interact. Basically, mostly based on their electric fields, their magnetic fields, and what's going on with the behavior of the electrons on the quantum level. That's beyond the scope of the class, Piper, so just pipe down back there. Okay, the type of spectroscopy that we're going to spend a lot of time talking about in the beginning is called nuclear magnetic resonance, abbreviated NMR. Let's take this apart a minute, make sure we understand what's going on here. The first word, of course, is nuclear, and in this context, it just means that it relates or pertains to the nucleus of the atom, where the protons and neutrons are. Oftentimes, when we use that word nuclear in everyday language, we're talking about a nuclear reaction. We're talking about the nucleus breaking apart. We call that nuclear fission, or two nuclei fusing together, nuclear fusion, or nuclear decay, which is related to radioactivity. That's, when the atom comes apart, that's a natural type of fission. So a lot of times in our everyday language, we're talking about nuclear reactors or nuclear weapons, or maybe what's happening inside the sun. Those are changes to the nucleus where the number of protons and neutrons in the nucleus changes. In this context, in NMR, we're not doing nuclear reactions. So we are talking about the nucleus, but the nucleus isn't changing. So this has nothing to do with radioactivity or nuclear weapons or what's going on inside the sun. The second part of our spectroscopy, magnetic, means we're talking about magnetic properties and magnetic fields. And so we're going to be using atoms that have a nucleus where the nucleus itself is magnetic. And finally, resonance. And the word resonance comes up a couple of different times. We actually talked a lot about, earlier in the year, resonance as relates to benzene. We talked about a resonance hybrid, where there's one true structure that's partway in between the two Lewis dot diagrams that you draw. In this context, it means something different. So this actually doesn't have anything to do with those double-headed arrows. In this context, we're talking about resonance in the physical aspect, right? That is the tendency of a system to oscillate at maximum amplitude. So for example, if you've ever pushed someone on a swing, swings have a resonant frequency. If you push the person on the swing too slowly, like one push every 30 seconds, they're not going to swing very high. If you push them too fast, if you give them like a push every second or a push every half second, that's too fast. You're never going to get them to swing really big swings, right? For most swing sets, and I can speak because I've had a lot of practice, the resonant frequency is somewhere around one push every 6 or 7 seconds. So you push and the person goes forward and then they come back and then you push them again, right? And if you do it just right, you can get them to oscillate, to go back and forth at the maximum possible amplitude. This is also related to opera singers that can break a wine glass with their voice. same idea, right? That glass, if you just tap it, has a resonant frequency. That's the natural sound it makes when you tap it with a knife or a fork, and it goes ding. If you induce that resonance frequency by exposing that wine glass to that same sound, you can actually make the atoms and molecules inside vibrate until the glass breaks or shatters. If you've heard of MRI, MRI is basically this exact same technology, but it's medical application, right? So when you do NMR to people, we call that MRI. And some of you may have even had an MRI. Basically, it's a way to look at the different tissues in your body. The water areas and the areas that are higher in protein or higher in fat have different resonant frequencies. And so you can kind of see what's going on inside of a person without cutting them open. Originally, they started talking to patients, and they were explaining that this was a form of nuclear magnetic resonance. And the patients went crazy because when they heard the word nuclear, they were like, oh, I'm going to glow in the dark. This is radioactive. Like, it's not safe. And so they changed the name from NMR to something that sounds much nicer, magnetic resonance imaging. See, doesn't that sound much nicer? I have to say that we're going to talk about sort of a slightly oversimplified version of this. And if you're interested in doing more research about what's happening on the quantum mechanical level in terms of the nuclei precession and the different quantum states, please feel free to do a little bit more research. But we're going to do one kind of half step down from that. All right, first, let's talk a little bit about quantum spin. You might have talked last year in intro chem about electron spin, especially if you drew little boxes like this. So electrons have this form of angular quantum momentum, and it's quantized, right? So they can't sort of spin in any way they want to. Electrons have two spin states. We say that they are a spin 1/2 particle. So electrons can either be spin up or spin down. And you might remember some rules about sort of how they orient themselves or distribute themselves in different orbitals and different energy levels and sublevels. So that's an example of spin in the electron context. As it turns out, the nucleus itself, where the protons and neutrons are, it can also have a form of quantum spin. The most common nucleus we use in NMR is the hydrogen nucleus, and specifically H1. H1 is the most common form of hydrogen. Well more than 99.99% of all hydrogen in the universe is H1. H1 just means it's one proton and 0 neutrons, so that the total mass number is 1. We also sometimes use carbon-13. Carbon-13 is not the normal isotope for carbon. About 99.8% of all carbon is actually carbon-12, but there is a little bit of carbon-13 that's naturally occurring. Did I get that number right? It's about 1.1% carbon-13 and about 98.9% carbon-12. Anyhow, we're going to focus mostly on hydrogen-type NMR. There are also a lot of common isotopes that are found in organic compounds like carbon-12 and carbon-16. They're actually spin 0, and so you cannot do NMR on normal atoms of carbon and normal atoms of oxygen. It just doesn't work. But like I said, that's okay because we're going to use mostly the hydrogen atoms. All right, a little bit more about nuclear spin. A normal hydrogen nucleus, and if you think about what H1 is, remember the hydrogen nucleus is just a proton. It's one proton and 0 neutrons. And if it's a neutral atom, there's also an electron. But of course, the electron is not in the nucleus. So an H1 nucleus is basically just a proton. It has a quantum spin of 1/2, but you only observe that in the presence of an applied magnetic field. So if you don't put your sample of hydrogen in a magnet, right, those different nuclear spins are just pointing every which way, right? So the little plus signs here, the plus signs represent the hydrogen nucleus, the proton, and these arrows represent the direction in which their magnetic moments are pointed, right? So the fact that they have spin 1/2 means that they act like little magnets, only without an external applied magnetic field, they're just pointing all over the place. If instead you take that sample that has hydrogen in it and you put it inside a magnetic field, right? So you make either you have a permanent magnet or an electromagnet, and you put your sample of hydrogen in there. Now suddenly, all the hydrogen nuclei will act like little mini bar magnets, and they will either line up with the magnetic field in the same direction, we call that spin up or spin plus 1/2, or they will line up against it, and that will be spin down or spin minus 1/2. So the big arrow represents the direction of the applied magnetic field, and all of these are our little hydrogen atoms. And you can see there's actually slightly more of them lined up in the same direction of the field as against it, but they're all lined up either with it or against it. And I just mentioned that, right? The spin up is actually the slightly lower in energy. So at most temperatures, especially around room temperature, you're going to get slightly more hydrogens lined up in the spin up state than in the spin down state. Now, here is something interesting. Not only do these hydrogens line up with the magnetic field or against it, you can also make them flip up and down. And this is actually something that is probably 80 years old at this point, this technology. There were 3 physicists, Raby, Bloch, and Purcell, and they did a bunch of experiments during World War II and immediately following, and they realized that nuclei like the hydrogen nucleus, if you put it in an applied external magnetic field, you can make it flip up and down or down to up when you shine just the right kind of light on it. So here on the left is representing a hydrogen nucleus that is spin up in the same direction as the magnetic field. If you blast it with light, and in particular, the resonant frequency happens to be in the radio wave part of the spectrum, the hydrogen nucleus flips from up to down. The frequency that is used, the light frequency that's used to make this happen is called the resonant frequency. And as I mentioned, it was a form of radio waves. And early NMR experiments had resonance frequencies, depending on exactly what sort of external magnet they used, of somewhere between 30 megahertz and 90 megahertz, which is, if you listen to FM radio, that's between 30 and 90 on your FM dial. This particular resonance frequency has a name. It's called the Larmor frequency. Right? So the Larmor frequency is that precise frequency that causes a nucleus to resonate. And by resonate, we mean to flip from spin up to spin down. This is called a spin flip. So if you have a hydrogen nucleus, you blast it with its Larmor frequency, it will flip up and down, or down to up. And this is the equation that you can use to calculate the Larmor frequency. Nu equals gamma times b over 2 pi. So let's take that apart for a minute. This thing on the left, looks like a V, but that's actually the Greek letter nu, and we're using nu to symbolize frequency. So nu is the Larmor frequency. This is that precise frequency of radio waves that's going to make that hydrogen spin from up to down. So the frequency is equal to gamma times b over 2 pi. Well, b we're using as the strength of our applied magnetic field. Right? So the stronger the magnetic field, the stronger the magnet we're using for our experiment, the larger the Larmor frequency. Gamma, that little squiggly guy, this is a lowercase Greek letter gamma, is what's called the magnetogyric ratio. And that's related to the magnetic character of each nucleus. All that's saying is that it basically is a number that tells you how good of a magnet that nucleus is. So H1 has a different magnetogyric ratio than, for example, C13, but all H1 nuclei have the same magnetogyric ratio. So essentially, it's just a constant, right? So this is a constant. 2 pi, of course, is just a constant. If this is a constant and that's a constant, what do we notice about the Larmor frequency? It is, in fact, directly proportional to the strength of the magnetic field, right? For a given nucleus and a given magnetogyric ratio, the Larmor frequency depends only on the strength of the applied field. The bigger the applied field, the higher the frequency. So, physicists did a bunch of experiments in their fancy new spectrometers. And what they noticed was that when they tested different batches of compounds that contained hydrogen, they had basically the same Larmor frequency. So they put in some water. Water, of course, has hydrogen in it. They test its Larmor frequency, jotted that down, pulled out the water, put in some ethanol, put in some acetone, put in some propane, lots of different compounds. They all have hydrogen. The Larmor frequencies for hydrogens were all basically the same, right? The differences were mere parts per million, right? So they were almost exactly the same, except for little teeny tiny differences. And the physicists were super excited about that. They were like, this is amazing. There's this cool universal thing about hydrogen. It has this Larmor frequency, and we can measure it, and it's cool, and it's awesome. And chemists were like, huh, that's interesting. I mean, it's interesting that this happens, sure. And it's interesting that their Larmor frequencies are very, very, very similar. But why are they not identical? Right? Why do these small differences exist? What causes them? And more importantly, what can they tell us about these different chemical compounds? Because if water has a different Larmor frequency than propane, and propane has a different Larmor frequency than acetone, why is that? And what does that tell us about water or propane or acetone? And can we use this to our advantage? So in my next video, I'm going to talk about what is the significance of this little tiny difference, and how can we use that difference and use those things to get some information about the chemistry of these different compounds. So stay tuned.